In this video lecture, we will try out VectorDB hands-on and see how it helps large language models. First, let's understand some of the key concepts. Let's understand vector databases and how they work together with large language models. In the world of machine learning, think of a vector as a one-dimensional container for data. Vectors can only handle elements of the same type. That means they're all either numbers or strings, but not both. And when you need to access a specific piece of data in a vector, you just refer to its index. In machine learning and natural language processing, we transform human language into machine-readable numerical values and store them as numeric vectors. These vectors capture the structure and semantics of the original text. After processing the data and making predictions, there comes a crucial step: converting the vector representations back into their original text form. This conversion allows us to understand and interpret the results in a human-readable format. Some of the popular techniques are bag of words models or TF-IDF models. Bag of words or TF-IDF creates sparse matrices based on number of unique features or words. Word embedding and sentence embedding are other techniques used to create the numeric vector format of text. Word embedding is a technique used in natural language processing, NLP, to represent words as dense vectors in a high-dimensional space. Each word is mapped to a unique vector, capturing semantic relationships between words. For example, in a word embedding model, similar words are represented by vectors that are closer together in this space. For instance, consider the words king, queen, and royal. In a word embedding model, these words might be represented by vectors like this. Notice that the vectors for king and queen are closer to each other than they are to royal, reflecting the semantic similarity between king and queen. Also, the advantage of these dense vectors over sparse matrices in bag of words or TF-IDF model is their ability to capture more nuanced semantic relationships and context due to their continuous and compact representation. Sentence embedding extends the concept of word embedding to entire sentences. It represents entire sentences as fixed-length vectors, capturing the meaning and context of the text. This allows us to compare and analyze entire sentences in a continuous vector space. In vector space, sentences with similar meanings are closer together, reflecting their semantic similarity. Vector representation could look something like that. These vectors are hypothetical and used for illustration purposes. In practice, word embeddings are typically high-dimensional to capture richer semantic relationships. These three sentences are closer in meaning, so the distance between them is less in vector space. Similarly, the same applies to the other two sentences. Sentence embedding is utilized in large language models, LLMs, to capture the semantic meaning and context of entire sentences, enabling more comprehensive understanding and generation of human-like text. Another advantage of using sentence embeddings in large language models is their ability to handle variable-length inputs more effectively, allowing the model to process and generate coherent text across different sentence lengths. Sentence embeddings are also valuable for searching and querying large text corpora efficiently. By converting sentences into fixed-length vectors, similarity measures such as cosine similarity can be applied to quickly find relevant documents or sentences within a corpus, facilitating tasks like information retrieval and document ranking. High-dimensional vector embeddings are stored in a vector database to facilitate efficient retrieval of similar objects. Vector databases employ advanced indexing techniques to map high-dimensional vectors to specific data points, enabling the rapid implementation of intelligent search algorithms for efficient and effective retrieval. Efficiently searching for similar items serves as a crucial requirement for augmenting prompts with contextual data in generative AI, notably in large language models. Some of the advantages include easier searching with semantic search support and quick retrieval using indexing for vectors. Additionally, large datasets are efficiently handled with bulk data loading, and fault tolerance is provided through clustering. Some drawbacks include not fully supporting traditional queries and transactions and lacking built-in functions for data manipulation. Plus, inserting large datasets might cause delays due to index processing, and it could be memory-intensive, possibly requiring a GPU for better performance. Now let's look at large language models, or LLMs. Let's look at a sample sentence. In large language models, LLMs, we input text into the neural network, one word at a time, and the model predicts the next word in the sequence. To accomplish this, the model must accumulate knowledge about the world and beyond. Vector databases assist in efficiently searching through large collections of text data by representing words or phrases as vectors in a high-dimensional space. This enables the language model to quickly find similar words or phrases during the prediction process, enhancing its ability to generate coherent and contextually relevant text. Vector databases play a pivotal role in bolstering the capabilities of large language models, LLMs, across various domains. Firstly, in the realm of context retrieval, vector databases facilitate the efficient retrieval of relevant contextual information. By storing words or phrases as vectors in a high-dimensional space, vector databases enable LLMs to quickly identify and retrieve contextually similar words or phrases, thereby enhancing the model's understanding of the surrounding context. Vector databases play a crucial role in querying and retrieving similar information from a knowledge base, eliminating the need to use sensitive enterprise data for training or fine-tuning large language models, LLMs. Questions are converted into LLM-specific embeddings, which are then used to fetch relevant context or documents from the vector database. This context is incorporated into the LLM prompt, enabling accurate response generation. With enterprise-specific context, LLMs can deliver precise outputs. Use cases include document discovery, chatbots, and Q&A systems. Key benefits include avoiding the use of sensitive data for model training, cost-effectiveness compared to LLM fine-tuning, and almost real-time updates to the knowledge base. Secondly, vector databases contribute to the memory of LLMs by providing a structured framework for storing and accessing information. By organizing data into vectors and employing efficient indexing techniques, vector databases allow LLMs to effectively retain and recall previously encountered information, augmenting the model's ability to generate coherent and contextually relevant text. Functioning as long-term memory for large language models, LLMs, vector databases enable the retrieval of the last N relevant messages from entire chat histories, spanning multiple sessions and interactions. This capability surpasses the token length limitations of LLMs, granting users greater control over conversations. Here's how it works. When a user poses a query, the system retrieves the stored embedding from the vector database and passes it on to query the LLM. The LLM generates a response, which is shared with the user, and the response embedding, along with the conversation history, is stored in the vector database. This approach finds application in knowledge discovery and chatbots, offering benefits such as bypassing token length limitations and facilitating smooth conversation topic transitions. Additionally, vector databases play a crucial role in LLM caching mechanisms. By storing frequently accessed vectors in a cache, vector databases enable LLMs to expedite the retrieval process, thereby improving overall performance and response times. Implementing a cache for previous large language model LLM queries and responses enhances efficiency and conserves computational resources. Here's how it works. When a user asks a question, an embedding is generated and a cache lookup is performed. If the information is found in the cache, a response is provided without invoking the LLM. If the information is not cached, the LLM is invoked and the response is stored in the cache for future use. This approach benefits all use cases, including document discovery, information retrieval, chatbots, and Q&A systems, by speeding up performance and optimizing computational resources and LLM invocation costs. This integration of vector databases into LLM architectures significantly enhances the model's proficiency in understanding context, retaining information, and optimizing performance across various tasks and applications. You need to incorporate vector databases into models and MLOps to ensure optimal model performance, even at increased scale. This may require reassessing the data pipeline to enable real-time or near real-time predictions, fraud detection, recommendations, and search results. Vector databases helps with optimizing security, cost, and performance across use cases while using LLM. LLMs like GPT-4 convert raw data into high-dimensional vectors for semantic understanding. Vector databases efficiently store and retrieve these vectors, crucial for applications like chatbots and recommendation engines. While LLMs benefit from context injection, there's a limit to the input size. Vector databases enable efficient retrieval, enhancing their reasoning abilities. These databases support long-term memory for LLMs, crucial in enterprise AI applications. They handle diverse data types, fostering innovation and insights, and enable real-time applications with flexibility. Vector databases treat vectors as primary entities, allowing seamless semantic searches among unstructured data. They empower nuanced natural language understanding alongside LLMs, though challenges in contextual awareness persist. There are many open-source and licensed vector databases. Milvus is a powerful open-source vector database, ideal for efficiently managing and searching large-scale vector data. It offers various similarity search algorithms and supports both CPU and GPU acceleration. Similarly, Vespa is a versatile open-source big data processing engine designed for real-time data processing and analytics tasks. It provides built-in support for search and recommendation systems, making it a valuable tool for handling large-scale data processing tasks with ease. Okay, now let's dive into the practical side of using a vector database. We're going to use Chroma, which is a popular open-source vector database. With ChromaDB, you have two options for storing data. You can either use their default embeddings, or you can generate embeddings for your documents using OpenAI's embedding model. We'll give both methods a try. Let's head to the OpenAI website to explore their embedding model. If you're new to OpenAI and want to learn how to use their API, check out our other video linked in the description. Click on Embeddings. We'll be using the Text Embedding 3 Small model. You'll find a sample curl command demonstrating how to invoke it. Next, let's head over to Colab and write the equivalent code in Python. We will install OpenAI. Then from OpenAI, we will import OpenAI. Define the key, endpoint, and headers. Make sure you use your own key. Now let's try to create embedding for a sample sentence. We can see the vector representation. Now we will have 5 sentences and create their embeddings and store them in the Chroma database. This is our list of embeddings for 5 sentences. Now we will install ChromaDB and create a collection. Collections are where you'll store your embeddings, documents, and any additional metadata. You can create a collection with a name. Now we will store the embeddings in the collection. Then we will have a new sentence with the word future. Convert it into embedding using OpenAI and use that embedding to query the collection. It should find the document containing the word future. That is, artificial intelligence is shaping the future. Next, instead of using OpenAI embedding, we will use the default embedding. Chroma will store your text and handle tokenization, embedding, and indexing automatically. And search with the text this time, instead of embedding, as this search string will also be converted to embedding by Chroma, and search will be performed. You will find the source code in the description. Try it out yourself. Thank you for watching. Please subscribe for more informative content on cloud, data, AI, and generative AI. Hit the bell icon to receive future notifications. Check out our popular Udemy course on Big Data, Hadoop, and Spark, linked in the description.